Okay, welcome to lecture 3 in week 3 of Machine Learning Foundations. As you know, we are going to continue the discussion on topics in linear algebra. In particular, in this lecture, we'll be looking at the concept of projections, which are very, very important because they have a strong connection to least squares problems. And in this particular lecture, I'll be motivating the need for projections, and I'll take a simple example where we'll understand how to project onto a line. Now the idea that underlies projection onto a line can be easily extended to projection onto a subspace, for example the column space of a matrix, which we'll be looking at in the next lecture. But in this particular lecture we'll be looking at the need for projections, which will be motivated using solutions to linear system of equations in the case where they are inconsistent, and then we'll understand how to project onto a line. Okay, so welcome to yet another lecture on machine learning foundations. We'll continue the discussion on least squares, and but before that we'll be talking about projections. So today's talk is focused on projections, which has strong connections to least squares. So what I mean in terms of geometry, what you want to do is you have a vector, you have some other line, call this B, you want to project B onto X. This is a right angle, this point is P. In general, the more generalization is B is here and you have some linear space Ax. So, you want to project B onto the line through X, or more generally onto the column space of a matrix A. The important question is why project? What is the requirement or the need for projection? And this is the first question that we are going to answer. The second question is, given a basis for a subspace, say S, more concretely say spanned by columns of A, for example. Now, is there an easy way to calculate the projection P of P onto S? So, these are two questions that we are going to answer today. Let's look at question 1. Yeah, on 1. Suppose we are given data, say x1 b1 until x say n bn. For example, you could have a setup like 2x equals p1, 3x equals p2 and 4x equals p3, or something else, say x plus 2y equals 4, x plus 3y equals 5 and 2x plus 4y equals 6. Now, if you look at these systems, just look at these systems. These systems are inconsistent. There's no solution that satisfies this system of equations. Now if you want to look at the matrix view is you can make up a system of equations and inconsistent this is inconsistent if B does not belong to the column space of A. And in such situations it makes good sense to project B onto column space of A. So that's the thing. So this is the motivation. In many situations you are not able to solve Ax equals B because if you look at the columns of A, B is not there. B is not a linear combination of the columns of A. It can be outside the column space. And if there is no way to solve this equation, what is the next best thing you can do? The best thing you can do is you project. So let's start the discussion with projection onto something very simple. The very first figure that I had done, projection onto a line. So if you look up again, so I don't know if I can copy this again. So look at this figure, the very first figure. Let me call this figure 1. If you look at figure 1, remember this thing, or it may be worth drawing this again. You have B, you have X, and you have this 90 degree, and call this P, and call the rest as E. E equals B minus P. Now the projection P is some. I want to project this not onto X. Sorry, I want to project this onto A. Let me call this A. B equals some scalar multiple of A. Now the question is, which is the best? We know E equals B minus P equals B minus X hat A, and we know that E is perpendicular to A, which is like saying that B minus X hat A perpendicular to A, or the dot product, in this case it is just a straightforward product, is 0, leading to what? What is the solution for X hat? Just do this on your own, pause the video. Transpose B divided by A transpose E. Now what's the projection? Implies, okay, let me write it. Implies P equals X hat A, which is nothing but A transpose B by A transpose A into A. So that's projection onto a line. We'll move on to projection onto a space zone, but let's understand this projection business a little more carefully. In fact, as a slight detour, we can look at what is called Cauchy-Schwarz. Cauchy-Schwarz inequality. This is a very well known inequality with several proofs. We can show you, I will show you a short proof using projections. We know that this is the length of the vector E, which is here if you look at this figure, and that's a positive length quantity, and so I can write this as B minus P. This I know is greater than or equal to 0. Now let's substitute whatever we have learned. Just recall P is this, so I can write B as B minus A transpose B divided by A transpose A into A the square, and this is nothing but just A minus B square. It's square of the first minus 2 times A transpose B square divided by A transpose A plus A transpose B by A transpose A square into A transpose A. Now this can be reordered as B transpose B into A transpose A minus A transpose B square divided by A transpose A. And we know that this is non-negative, which just implies B transpose B, the numerator is non-negative, it just implies B transpose B into A transpose A is greater than equal to A transpose B square, or A transpose B absolute value is less than equal to the length of A into the length of B, and this is Cauchy-Schwarz. This is Cauchy-Schwarz inequality, and reasonably short proof at that. So, moving on, we will look at what is called the projection matrix. Recall P was A into, we wrote it this way, A transpose B by A transpose A into A, which I can write as A into A transpose divided by A transpose A into B. Let this capital P be defined as this matrix A into A transpose divided by A transpose A. Then projection of B onto A is just P times not B A. So, if I want to project any vector, then I just have to left multiply by to project any vector B, just left multiply by the projection matrix. Okay. Simple enough thing. So, let us look at a quick example, a simple one. Imagine you are looking at this vector 1 1 1. What is the projection matrix? The projection matrix is A into A transpose divided by A transpose A. Just pause the video for your own benefit, work this out by hand on your own. I am going to give out the answer. It is going to be 1 by 3 into 1 1 1 1 1 1, which is just the matrix with all 1 by 3 entries. So, that is your projection matrix. Now, in this particular case, observe that the matrix P is symmetric, and this is something you can also see. The second thing that you can see is P square equals P, And this makes intuitive sense. What does left multiplication by P achieve? It brings it onto the line through A. And the next time if you project again, which is like PB is already on the line, if you project again, you are going to get back the same quantity. So P square has to be P simply because you already projected by doing P. Yeah, that is P square B equals PB. The idea is PB is already on the line through A. So, another round of projections won't change it. So, once you project, you are already wherever you want to be, say on the line A, and if you project again, it is not going to change anything. Yeah. Third thing, what is the column space C of P? If you look at this matrix here, the matrix given in the example above, then the column space of matrix is just the line through A. So, what is the null space P? This is nothing but the plane orthogonal to A. And what is the rank? Rank R P equals 1. The last thing that I want you folks to observe is this. If instead of projecting onto A equals 1, 1, 1, if I set A as 2, 2, 2, then what would be the projection matrix? You can go back and verify, it turns out to be the same as before. So, I would just say check this. So, either pause or do it later, plus do it once. The projection matrix won't change. It's the same line and projection won't change. So, right now the next thing we are going to do is we are going to explore the connection of this to least squares. Okay, quick summary before we end this lecture. In this lecture, we understood what it means to project onto a line, and even before that, we also understood why we need projections. The motivation was that there are several linear systems where like Ax equals B, where B is not in the column space of A, which just means that you cannot solve this system, which is the inconsistent case. But what's the best approximation you can arrive at? And a popular alternative is least squares, and to solve such least squares problems, an equivalent geometric idea is to do projections, orthogonal projections onto the column space of A. So, that's very important. So, projections are closely tied to least squares problems, and we also, as a side benefit in this course, we also saw a simple proof of Cauchy-Schwarz inequality once you understood what it means to project. In the subsequent lecture, we will generalize this idea of projection onto a line to the case where you want to project onto a subspace. In particular, we will be projecting onto the column space of a matrix, and we will use this idea to solve least squares problems and that you will see in the subsequent lectures.